This week's lesson focuses on inscribed angles and inscribed polygons. Specifically, we will try to answer these two essential questions. How are inscribed angles related to their intercepted arcs? And how are the angles of an inscribed quadrilateral related to each other? The first theorem we're going to look at is called the measure of an inscribed angle theorem. So let us recall that an inscribed angle is an angle whose sides are two chords of a circle. So in other words, segment AD is a chord, and so is DB. So that means they form the inscribed angle, angle ADB. How is that different from a central angle? A central angle will have its vertex on the center of a circle. But if the vertex of an angle is also a point on the circle, then it's called an inscribed angle. Now, an inscribed angle has a corresponding intercepted arc. And in this figure, the intercepted arc is the arc that is formed by A and B. Now, this theorem states that this yellow inscribed angle and the green intercepted arc are related to each other. So, in what way? We can actually write an equation of this form. Measure of angle ATB is equal to 1/2 times the measure of arc AB. So which is bigger and which is smaller? Since this angle is 1/2 of another quantity, the measure of the angle must be smaller than the measure of the arc. The next theorem that we're going to look at is called the inscribed angles of a circle theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. So let's try to identify them in the figure. The two inscribed angles are actually angle D and angle C. Now they intercept the same arc. So their common intercepted arc is this arc here, which is AB. Let me trace that one. Okay, so since the measure of an inscribed angle is actually 1/2 of the intercepted arc, if you get 1/2 of the same arc for both of these angles, then angle D and angle C will end up to be congruent to each other. In equation form, we can write angle ADB is congruent to angle ACB, and by definition of congruence, you can also put the small letter M in front of the angle sign and change the congruent sign to an equal sign. In this slide, we are going to define inscribed polygon. A polygon is an inscribed polygon when all its vertices lie on a circle. So let's say, for example, in this figure, the blue pentagon has all its 5 vertices on the circle. So that means it is an inscribed pentagon. The circle that contains the vertices is called a circumscribed circle. So the red circle, which contains all the vertices of the pentagon, is a circumscribed circle. In this figure, the inscribed polygon is now a triangle. Now, specifically, we're going to talk about the inscribed right triangle theorem. It says that if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. So, in other words, AC is the diameter because it contains the center of the circle. So, if this is a diameter, then this arc AC is actually a semicircle. So if it is a semicircle and angle ABC is the corresponding inscribed angle, we can find the measure of angle B by getting half of the semicircle. So since the semicircle measures 180 divided by 2, then angle B will be equal to 90 degrees. So if angle B is a 90-degree angle, that makes triangle ABC a right triangle. The converse is also true. If one side of an inscribed triangle is the diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is a right angle. In symbols, we can actually write it this way. Since it is biconditional, I'm using the phrase if and only if. So measure of angle ABC is 90 degrees if and only if segment AC is the diameter of the circle. So in other words, one side of the triangle has to be a diameter for the triangle to be a 90-degree triangle or a right triangle. And last but not the least is the inscribed quadrilateral theorem. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So in this figure, all the vertices D, E, F, and G, which are the vertices of the quadrilateral, lie on circle C if and only if D and F is equal to 180, and at the same time, E and G also must sum up to 180. In other words, angle D and angle F must be supplementary, and E and G must also be supplementary. So if there are two pairs of angles that are supplementary, what does that tell you about the sum of all the angles of this quadrilateral? Well, if a pair is 180 and the green pair also make 180 degrees together, it means that if you add all of them up, it's 2 times 180 degrees, which is consistent with what we know about quadrilateral, which is all the angles in a quadrilateral is actually equal to 360 degrees. So those are the important theorems for this lesson, and you will see another screencast later on showing you more examples on how to use these theorems in computation.